Hello everyone, welcome to the course of ultrasonic testing technology. This class continues to explain the quantitative knowledge of ultrasonic testing defects. Through the study of this class, we hope to achieve the following teaching objectives. Grasp the classification of ultrasonic flow quantification methods. Master the factors that affect the defect quantification of ultrasonic testing. In last lesson, we explained the adjustment method of ultrasonic testing sensitivity and the most commonly used defect quantitative method, equivalent method. The equivalent method is mainly used when the defect size is smaller than the cross-section of the sound beam. This lesson will continue to explain other methods of ultrasonic flow quantification. Bottom wave height method. It refers to measuring the relative size of defects by using the relative wave height of defective wave and bottom wave. It cannot accurately measure the equivalent size of defects. When there is a defect in a workpiece, because the defect reflects part of the ultrasonic beam, the caustic beam reaching the bottom of the workpiece is reduced, resulting in the reduction of the height of the bottom wave of the workpiece. The larger the defect, the higher the defect wave, the lower the bottom wave, and the greater the ratio of defect wave height to the bottom wave height. The bottom wave height method usually uses the following methods to represent the relative size defects. FBF method is measure the relative size of defects by the ratio of defect wave height F and bottom wave height BF as defect under certain sensitivity conditions. FBG method is to measure the relative size of defects by the ratio of the defect wave height F to the bottom wave height BG at a defect-free location under certain sensitivity conditions. BG or BF method is to measure the relative size of defects by the ratio of the height of the bottom wave BG as a defect-free location on the height of the bottom of wave BF as the defect location under certain sensitivity conditions. The bottom wave height method does not need to attach the block. It can directly use the bottom wave to adjust the sensitivity and compare the relative size of defects, which is easy to operate. In addition, the bottom wave height method is only applicable to workpieces with parallel upper and lower surfaces. Length measurement method. It refers to the defect quantitative method generally adopted when the defect size in a workpiece is larger than a beam section. The length measurement method is mainly used to determine the flow size according to the flow wave height and the probe movement distance. The defect length measured by the specific method is called the indication length of the defect. Because the orientation, property, and surface state of defects in the actual workpiece will affect the echo height of defects. The indication length of defects is always less than or equal to the actual length of defects. According to different sensitivity standards, when measuring defect length measurement methods can be divided into relative sensitivity method, absolute sensitivity method, and endpoint peak value method. Relative sensitivity length measurement method, with the highest echo of the defect as the relative reference, move the probe along the length direction of the defect, and reduce the certain dB value to measure the length of the defect. The sample values reduced include 3 dB, 6 dB, 10 dB, 12 dB, 20 dB, etc. The 6 dB method and the 6 dB method at the endpoint are commonly used. 6 dB method, as the wave height is reduced by 6 dB, it is exactly half of the original, so 6 dB method is also called half wave height method. Its specific method is to move the probe to find the highest reflected wave position of the defect, and then adjust the attenuator to adjust the defect wave height to the reference wave height. Then move the probe to the left and right along the defect direction until the defect wave height drops to half of the reference wave height. And the distance between the probe center lines is the is the indication length of the defect. 6 dB method is a common method for defect length measurement. It is applicable to the length measurement when the defect wave has only one high point during scanning. Endpoint 6 dB method. When the reflected wave height of each part of the defect changes greatly, the endpoint 6 dB method is generally used for length measurement. The specific method of endpoint 6 dB method for length measurement is that when the defect is found, the probe moves left and right along the defect direction to find the highest reflected wave at both ends of the defect. Based on the reflected wave height of these two endpoints, respectively, and continues to move the probe to the left and right. When the reflected wave heights to the endpoints are reduced by half, the distance between the probe center lines is the indicated length of the defect, as shown in the right figure. This method is applicable to the length measurement when the defect reflection wave has multiple high points during scanning. Absolute sensitivity length measurement method. When the instrument sensitivity is certain, the probe moves in parallel along the flow length direction. When the flow wave height drops to the specified position, the distance the probe moves is the indicated length of the flow. This method is often used in defect length measurement in automatic inspection. Endpoint peak value method. In the process of length measurement and scanning, if the peak value of the reflected wave of the defect fluctuates and there are multiple high points, the moving length of the probe between the maximum values of the reflected wave at both ends of the defect can also be used as the indication length of the defect, as shown in the figure. This method is called endpoint peak method. From the operation mode of this detection method, it can be seen that the defect length measured by the endpoint peak method is smaller than the indication length measured by the endpoint 6 dB method. Therefore, this method is generally only applicable to the length measurement when the defect reflection wave has multiple high points in the scanning process. Factors affecting defect quantification. At present, A-type display pulse reflection ultrasonic flow detector is widely used in industrial ultrasonic flow detection, which is mainly used to quantify defects based on the reflected wave height of defects. Therefore, all factors affecting the wave height of defects will affect the accuracy of defect quantification. The main influencing factors include the following aspects. Performance of instrument and probe. The performance of the instrument and probe directly affects the echo height of the defect. The performance that mainly affects the defect quantification includes the vertical linearity of the instrument, the accuracy of the attenuator, the frequency, the form of the probe, the size of the chip, the size of the refraction angle, etc. Workpiece. The influence of workpiece on defect quantification mainly includes geometric shape and size of workpiece, the surface state and attenuation of ultrasonic wave. Coupling. The purpose of coupling is to make ultrasonic wave enter the workpiece smoothly. Different couplant and coupling layer thickness will affect the ultrasonic transmission. When the thickness of the coupling layer is an integral multiple of the half-valve enough, the sound intensity transmissivity is independent of the properties of the couplant. For the given couplant, when the thickness of the coupling layer is equal to, as we can see the formula, when the acoustic independence of the couplant is the geometric mean value of the acoustic independence of the medium on both sides, the ultrasonic transmissivity is the highest. Therefore, the difference of coupling effects will lead to the difference of echo height. Defects. The types, sizes, surface roughness, orientations, etc. of defects in the actual workpiece are various. And the reflectivity of ultrasonic wave is different. Therefore, the properties of the defects will also affect the quantitative results. In the actual testing process, the quantitative results of defects obtained should be the results under a combined influence on the above factors. Therefore, when quantifying defects, we should comprehensively consider various influencing factors and carefully analyze them in combination with specific conditions to improve accuracy or quantification. Well, that's all about the quantitative knowledge of ultrasonic flow detection. There are relatively many contents. I hope you can strengthen your review and understanding after you get done. See you next time.